Good morning and welcome to lesson number 1 in Unit 2A, Quadratic Functions, Forms, and Transformations in our grade 11 University College math class. This is analyzing quadratic functions. So the way that we've done this is we've taken Unit 2, which has sort of two major components, forms and transformations, and we divided it up into Unit 2A and Unit 2B. So Unit 2A is the transformations portion, I guess, and Unit 2B would be the forms portion. So we're working through the transformations portion at the moment. We're dealing with quadratics, obviously from the title. So let's just have a quick look at just some information about linear equations and quadratic equations, which is right at the beginning here. As we would recall from both grade 9 and 10, linear equations can be expressed in this form here, y equals mx plus b. They produce straight continuous lines. Quadratic equations, and there's a few different forms. This one here is standard form, if you'll remember that from grade 10. It has a quadratic or a squared term in it, which you can see there with the exponent 2. The shape that they create is called a parabola, and yeah, that's it. So this introductory lesson is really, there's a few things going on, but one of the things we go over here is just a review of how to distinguish linear from quadratic functions. How do you tell them apart? So we're going to first look here at first and second differences. As you recall, first and second differences, that's what you calculate when you are looking at the output values for a function or relation. You look at the output values and then you compare their differences. And if they are constant, it tells you certain things about the function. So let's go over the first one here. The equation we've been given is y equals 3x plus 1. I'm just looking in the table here, and we are going to actually evaluate this for these input values here. Now you notice here that we're using y's. We could be using f at x as well. F at x equals blah. If we were so inclined, we could be employing function notation here. We didn't, and that's okay too. So here we have y equals 3, and in the place of the x, we're substituting in negative 2. There's our plus 1, and we'll evaluate this, so that'll be negative 6 plus 1, and that'll give us negative 5. And we're just going to go down the line and just do this. If you want to work ahead, that's fine. I'm going to just write them out as we go. So here we have negative 3 plus 1 is going to be negative 2. 3 times 0 plus 1 gives us 1. 3 times 1 plus 1 gives us 4, and 3 times 2 plus 1 gives us 6 plus 1, which is going to be 7. All right, so that is the completion of the ordered pairs, and now we're going to calculate the first differences. So first differences are calculated by taking the value that's lower down in the table, so negative 2, and then we subtract. That's the difference part. When we're talking here about differences, that's the difference. Minus 5. Now, as you know, two negatives bumping up with no number in between, that will be a plus. So our first difference here would be negative 2 plus 5, which gives us 3. And we're going to work down the line on that. So here we have 1 minus minus 2, or 1 plus 2, which gives us 3. Here we have 4 minus 1 gives us 3. And we have 7 minus 4 gives us 3. So what do we know here? The first differences, so what is true about the first differences? They're the same. Thus, for linear functions, the first differences are constant. Oops. Constant is the word that we want to be using here. Constant first differences tell you that you're dealing with a linear function. So that's first differences. You can apply first differences to any table of values and sort of get some insight into, more specifically, I guess, what you don't have. But in this case, because we ended up with constant first differences, 3, 3, 3, 3, that we know this is going to be linear. With quadratic, it's a little bit different. So let's work down the line on the quadratics. Same idea here. We have a quadratic equation. We can see it. We could also be using f at x here. Chose not to. That's fine too. And now we're going to substitute in our input values. So that will be 3, negative 2 squared minus 2 times minus 2 plus 1. I'm definitely going to run out of room here. All right, let's see if we can do some or most of this in our heads. So here we have 3 times 4, and that's plus 4, and there's a plus 1. So 3 times 4 is 12, 12 and 4 is 16, and another 1 is 17. So there you go. Let's try the next one. 3, maybe I'll write that a bit higher up there. 3, negative 1 squared minus 2 minus 1 plus 1. So that will give us 3 times positive 1 plus 2 plus 1. So 3 times 1 is 3, plus 2 is 5, and plus another 1 is 6. There we go. Let's keep working. 3 times 0 squared minus 2 times 0 plus 1. I don't even need the second row. The first term and the second term will become 0, so we're just going to have a nice easy plus 1 here. Let's work down the line. So we have 3, 1 squared minus 2 times 1 plus 1. So we have 3 times 1 minus 2 plus 1. So we have 3 minus 1, or sorry, rather 3 times 1, which is 3, minus 2, which is 1, plus another 1 is 2. And we have, lastly, 3 times 2 squared minus 2 times 2 plus 1. This will give us 3 times 4, which is 12, minus 4, which is 8, plus 1, which is 9. All right, so there's our table of values. Nothing too fancy that we're seeing there. Hard to interpret the tables. That's just not something our brains are really good at. So that's why we use things like first and second differences. So let's do the first differences here. We have 6 minus 17. Again, I'm using the value lower down in the table, subtracting the value higher up. Doesn't matter what those numbers are. It's always the value sort of lower down in the table or sort of further along, I guess, in the function. So 6 minus 17 gives us negative, oops, that's a highlighter, negative 11. And next down the line, we have 1 minus 6 gives us negative 5. And we have 2 minus 1, which gives us 1. And we have 9 minus 2, which gives us 7. Okie doke. First differences are not constant. So what does that tell us? Just one thing at this point. This is not going to be a straight line, which we can probably tell by the table of values. Now we're going to tackle second differences. Second differences, same as first differences, except instead of doing it from those original y values, we're going to be calculating our second differences based on our first differences. So what we have here is negative 5 minus negative 11, which is negative 5 plus 11, which is 6. Here we have 1 minus 5, or 1 plus 5, which is 6. And here we have 7 minus 1, which is also 6. So here we have constant second differences, which we can see. What's true about the second differences? They're the same. So what can we say about quadratic functions? That the second differences will be constant when calculated. So there you go. That's a bit of our proof of concept recap. Straight lines have constant, or linear functions, which are straight lines, have constant first differences, and quadratic functions, which make parabolas, have constant second differences. That's just something to sock away. Hopefully this review of how to calculate first and second differences was helpful. Let's move on. So from equations or from a table of values like we generated using first and second differences, that's how you can tell them apart. Another way to tell equations apart is by looking at what they call degree. Now we're not going to do this whole table because, again, it lends itself really well to a nice classroom discussion, but it's not essential for what we're doing. So the word degree, it is used to describe the type of function that you have. And the degree of a polynomial is determined by the value of the highest exponent in the equation. So if we look at something like this, y equals 3x plus 1, that's the one that we just did, we'll notice that we have some variables, and the largest exponent on any of the variables is just going to be 1. So that makes this a degree 1 function. The function has the name linear, and the constant differences would be first differences that are constant. And again, we're going to skip the sketch. It serves a purpose as we go through higher level function or higher degree functions, but it's not going to serve us any purpose today. Let's have a look at the next equation. So we have y equals 3x squared minus 2x plus 1. So again, we've got 1 here and a 1 here, and we also have a 2. So that's the highest exponent on any of the variables. That makes this a degree 2 function. We call that a quadratic, and it has constant second differences. Oops, that's an O. Second differences. And again, we're going to skip the sketch. All right, here's another one. Y equals negative 5x plus 4. Again, if we're looking down the line, the largest exponent on any variable is 1. That's going to make this a degree 1 function, which we call linear. And it's going to have constant, I'm getting lazy, constant first differences. Let's have a look at the next one. Y equals, so again, we've got our exponent of 1 on the variable y. However, we also have the exponent 2 on the variable x. So that makes this overall a degree 2 function, or a second degree function. We call those quadratic. And as we know, those will have constant second differences. Now these last two, again, we're going to skip them. It's a nice sort of illustration of concept, but we just don't need to spend any time on it. Let's finish up this video with just a little bit of terminology, and then we'll get to the graphing. So the last thing I want to talk about when we're talking about quadratics in general is just a review of a little bit of terminology. We're not going to read through it, but I'm going to highlight some of the stuff that's important. So when we're talking about quadratics, which are second degree functions with constant second differences, we use words like the direction of opening, because what it creates is a parabola, and a parabola has a direction of opening. If the a value, which is the value that sort of sits out front of the quadratic, the coefficient in front of the quadratic term, then our parabola is going to open up, and it'll look like something like that. Here we have an a value of less than 0, so a negative a value means that our parabola is going to open down. There we go. Another word that's important when we're dealing with quadratics is the vertex. Now the vertex is a very interesting and somewhat, well, it's important, but it's a magical point on a parabola. If you think of a parabola as a symmetrical shape, it just means that for every point on the parabola, it has a corresponding pair across the parabola from it, with the exception of the vertex. The vertex is the one and only point that stands alone. It's also the turnaround point, the point at which your vertex or your parabola changes direction. It starts going from upwards to downwards, or from downwards to upwards. Some of the words that we use when we're talking about a vertex are maximum, and we use this when our parabola is going to be opening down. As you can see here, this parabola would have a maximum point sort of at the top, a singular maximum point. And if we're talking about a minimum, we're talking about a low point that hits. And we get that when our parabola is opening up. Again, a single low minimum. How can you find the vertex? A couple of different ways. Again, we're going to spend time going over this when we are in the forms section, but the ways that you can find it are like by inspection, if you have a table of values. The other way is in this particular form right here. This is called vertex form. Now this will be new for some students, this particular form of a quadratic vertex form. For some students this will be new, and it has the vertex right in it. What I want you to note here are these two components. This h and this k, they correspond to the x and y values of the vertex. There's a cheat way to do it. We're going to skip over that until we actually get to the forms section of this unit. And last but not least, the terminology that I want us to grab right here is the axis of symmetry. And because this is a symmetrical shape, it has a line around which our whole shape is sort of divided, I guess, or rotated. And that corresponds to the x component of your vertex. And again, it's a dotted vertical line that you draw down your shape. So that's the end of the first part of this video. We're going to get back, work another example, and then we're going to do some domain and range, look at some other functions that are quadratics, and then you're off to the races. So that's the end of part 1. We'll see you in part 2.